Okay, so we'll start our tutorials directly by solving some problems from the textbook. These problems are a series of direct substitution. The textbook is Fundamentals of Fluid Mechanics, its 4th edition. Authors are Munson, Young, and Okishi. Right away, I'll start with problem number 1. So, an airplane moves forward in air with a speed of 500 miles per hour at an altitude of 40,000 feet. Find the Mach number when the temperature at 40,000 feet is minus 69.7 degree Fahrenheit. Gamma, or sometimes written on your formula sheet or in the textbook in K, is 1.4. And R, the gas constant, is 1716 feet-pound per slug. Degrees Rankine. Now, first things I need to do, I need to find the Mach number, which is given by V over C. V is my local velocity. C is the speed of sound. The Mach number is the degree of the compressibility. It's a measure, dimensionless measure of compressibility. Now, to find C is given by gamma RT. Gamma is not the universal ideal gas constant that we know. This is specific for the type of gas that it will be mentioned to you. In this case, it's for air. So this R is lambda over m, molecular weight. And this is the universal gas constant. However, this is specific with the type of fluid that we're using in the problem. Now, T is given in degrees Fahrenheit. I cannot use this when R is given in terms of Rankine. So I must convert T from degrees Fahrenheit. I add 460 and I will get T in degrees Rankine. Therefore, I have T in degrees Rankine is 460 plus minus 69.7 degrees R. Now C equals 1.4 times 1716 feet-pound per slugs degree Rankine times 460 minus 69.7, all under the square root, which gives me 968 feet per second. Therefore, my Mach number is the local velocity, 500, it's miles per hour. Convert that to feet per second, so I have 1 hour by 3,600 seconds. And every mile is 5,280 feet divided by 968 feet per second. So my Mach number is 0.757. So this is a subsonic flow. I'll go ahead to problem number 2. Determine the Mach number of a car moving in standard air at the speed of 25 miles per hour. Part B, 100 miles per hour. T, standard air, is 59.59 degrees Fahrenheit, which I'll convert it directly to degrees Rankine. I'm going to add 460, so I'd get T is 519 degrees Rankine. Okay, now in order to solve this problem, finding the Mach number, it's V over C. I am given the V's, I need to find C. C is gamma R T. For standard air, again, it will be given is 1716 for R. and for gamma is always 1.4, and for my T is 519. Therefore, my C is in feet per second, 1117 feet per second. C equals 100,117 feet per second. Convert that to miles, so I'll multiply it by 3,600 seconds per hour by 5,280 feet per mile. So I'm gonna get 761.6 miles per hour. Now, the Mach number at V equals 25 miles per hour, so that's case A. I will have Mach number is 25 miles per hour over 761.6 miles per hour. That's 0.0328. And part B, I have V is 100 miles per hour. Therefore, my Mach number is 100 miles per hour by 761.6 miles per hour, 0.131, dimensionless Mach number. Now, again, another direct substitution problem. Compare the values of speed of sound in meters per second at 20 degrees centigrade for air and helium. We're given the gas constant for air, 286.9 joules per kilogram Kelvin, and we're given for helium 2077 joules kilogram per Kelvin. Okay, so I must find the speed of sound. The speed of sound is always given by gamma RT. Okay, now RT is 20 degrees centigrade, which is 293 Kelvin. Now for air, I have C is gamma is 1.4, my R is 286.9 joules per kilogram Kelvin, temperature is 293 divided by 1 joule per Newton meter. In order to convert the whole thing to meters per second, 1 Newton second squared per kilogram meter, all under the square root. I'm going to have C equals 343 meters per second. Same problem for helium. I have C. This time my gamma is always the same, 1.4. I have 2077 joules per kilogram Kelvin. And my temperature is 293. Now for helium, the K is not given, but the real K or gamma is 1.66. So I must put here 1.66. Therefore, I will get 1005 meters per second. Again, I must divide this part by 1 joule per Newton meters and 1 Newton second squared per kilogram meter. All those conversions tricks we did in tutorial number 1, so you must check your notes. Now, problem number 3. What is the static pressure to stagnation pressure ratio associated with the following? A runner moving at 20 miles per hour, airplane moving at 500 miles per hour. In order to solve this problem, we must use our formula sheet and use the relation of the pressure at stagnation related to the pressure at any point. You should not be studying this by heart. So the formula is given by P naught over P is given by 1 plus gamma minus 1 over 2 Mach number squared gamma over gamma minus 1. If I rearrange this, I get P equals over P naught equals 1 over 1 plus gamma minus 1 over 2 Mach number squared gamma over gamma minus 1. Okay, so first things first, I'm asked to find the stagnation pressure ratio, static to stagnation pressure ratio, static to stagnation. So I have gamma, I need to find my Mach number. Mach number is V over C. C is gamma RT. Gamma is 1.4. R is given 1716 feet pound per slug Rankine. Also, the temperature is given 519 degree Rankine. We divide this by 1 pound per slug times feet per second squared to convert the whole thing to feet per second. So I would get 1117 feet per second. Because we're working in miles per hour, I'll convert it to miles. So that would be 3,600 seconds per hour by 5,280 feet per mile, miles per hour. Once I'm done, I can easily get my Mach number for each case. So for case 1, it's 20 miles per hour. Mach number is V over C. So I have 20 over 761.6. The answer is 0.0262. Substituting, I get P by P naught equals 1 over 1 plus 1.4 minus 1 over 2, 0.0262 squared, gamma over gamma minus 1. So the answer is 0.9995. For part B, it's 500 miles per hour. My Mach number is 500 by 761.6 miles per hour. It's miles per hour. So I'll get a dimensionless number of 0.656. Substituting that in P by P naught, I'll get 1 plus 1.4 minus 1 over 2, 0.656 squared. Gamma over gamma minus 1 can be considered 3.5. That's what it is, 1.4 over 1.4 minus 1. So the final answer is 0.749. All these problems are straightforward substitution problems. I'm just going over one problem from each type, and I'll be covered every type of problem that can possibly show up when it comes to direct substitution. Now we'll move forward. We have a bullet moving through air at 14.7 psi and 68 degrees Fahrenheit. Indicates a Mach cone of 28 degrees. How fast the bullet is traveling in feet per second and meters per second. So we have a bullet. Okay, and the bullet is creating a Mach cone of 28 degrees. Mach cone means here is the zone of action, and all of this part is the zone of silence. So if you're standing here, you would not hear the bullet. If you're standing underneath, you'd also not hear. You must be in this zone so that you can hear the bullet. As the bullet is going to move forward, eventually the mech cone will reach you and you'll hear the bullet. Now we're asked to find how fast the bullet is traveling. So we're asked to find V. Okay. Now Mach number when we have the mech cone is 1 over sine alpha, which is also equal to V over C. This implies V is C by sine alpha. V is gamma RT, and we are given sine alpha. Now, therefore V is gamma is 1.4, R is 1716, T is given in Fahrenheit, so I must add 460, so that would be 528. I divide by sine 28. I'd get the answer 2,400 feet per second. We'll start with part B because the question is already lined up for us to get the answer in feet per second. Meters per second, so that's part A, sorry. Part B, meters per second. We have V is 2,400 feet per second. We multiply that by 0.3048 meters per feet. So we'll get 732 meters per second. So this is one type of problem where you're actually given the angle and you're asked to find the velocity or the distance. So in this case we find the velocity. Now another mech cone problem. At the seashore, a high-speed aircraft moving overhead at an elevation of 10,000 feet. You hear the plane 8 seconds after it passes directly overhead. Using temperature of air of 40 degrees Fahrenheit, estimate Mach number and speed of aircraft. So we have an aircraft. It is creating a mech cone. And it's flying right overhead at this point. This is the angle of the cone. This is the height, elevation Z. And this is the distance X, which is velocity times time. So to make things clear, let me put this here. This is it. Okay, so I'm asked to find the Mach number and the speed of the aircraft. Okay, so the Mach number is 1 over sine alpha, which is V over C. This implies my V is C sine alpha. That's 1. Number 2, tangent alpha is opposite over adjacent, so that is Z over VT. Now, tangent alpha is also sine alpha over cos alpha, which is equal to Z over VT. I will replace my V here, so I'm going to get sine alpha over cos alpha is Z sine alpha over CT. I'll cancel my sine alphas. I'm going to get cos alpha is CT over Z. Therefore, alpha equals cosine inverse of ct over z. Okay. Now we need to find c. As usual, it's gamma RT. Those will always be given 17, 16, and my gamma is 1.4, and my temperature is 40 plus 460, so it's going to be 500. So that gives me 1096 feet per second. Therefore, alpha is equal to cosine of inverse 1096 feet per second times 8 seconds over 10,000 feet. So alpha is 28.7 degrees. Now I can get my Mach number is 1 over sine 28.7 degrees, so that's 2.08, and V equals Mach number times C. So my Mach number is 2.08 and my C is 1096 feet per second, so the velocity is 2280 feet per second. So these are most of the types of the direct substitution problems. They are very simple. It might have been boring, but I had to go through one problem so that I cover most of the topics.